So what are we looking at here? According to the given article about the body composition of the fetus, it's measuring the velocity of growth from the 15th week of gestation all the way to the 25th week of postnatal life. And as you can see, it's measuring two different subjects. The solid circles represent the fetus, and the open circles represent the placenta. So since it's a little bit jumbled up together, we had to separate them into two different scatter plots to observe them separately. With Excel, we were able to plot our best estimations for each data point onto two separate scatter plot graphs, as so. And you may notice some similarities between the two graphs, but what does this mean? To start, the green lines represent the polynomial degree of 1, or as we formally know it as a linear function, that give us a general fitting of the data's directionality, whereas the orange curves on both graphs represent the polynomial degree of 4, or as we formally know it as a quadratic function, to give us a better, more accurate fitting of the data's curvature. And you also notice that there's two equations shown at the bottom of the graphs. So the small equation shown in the corner over here represent the linear equation, as well as the r-squared values displayed at the bottom of it, whereas this whole long equation at the bottom represent the polynomial equation into 10 whole decimals, as well as the r-squared values displayed below them. So instead of observing the data on scatter plots, let's transfer them into decimals graphs. And in order to do so, we just copy the polynomial equation shown at the bottom of both graphs. After copying and pasting the polynomial equations on a decimals graph, the green and red functions that you could see here represent the polynomial equations plotted. However, the blue function on both graphs represent its derivative plotted. And you're probably wondering why we're doing this in the first place. Well, in order to figure out when exactly the growth rate of the fetus and placenta don't change at all, or if you want to get technical in a mathematical sense, where the slope of the tangent line is 0, or when the concavity changes on becoming a min or a max, we have to find the inflection points of the function, and which will also ultimately show where the derivative will cross the horizontal axis, shown on both graphs. After finding the inflection points of the data, another concern sparked pertaining to such data is what is the initial weight of the fetus and placenta. And in order to find that, we take the antiderivative. The reason being is that the polynomial equation we plotted in our decimals graph represent w prime sub f of t representing the fetus, or w prime sub p of t representing the placenta. In other words, it's measuring a particular unit, which in this case is grams, with respect to another unit, which in this case is days, or time. In order to find the initial weight, we take the antiderivative and work our way backwards by finding not prime, or double prime, whatever. We find just w sub f of t, which is the fetus, of course, and then w sub p of t for the placenta. Or in other words, just grams, with respect to no other unit, just itself. Antiderivative equation, we simply just plot it into a decimals graph and observe the difference. So let's start with the fetus. So with respect to 112 days, or 16 weeks for this matter, the fetus is about 9,000 grams. I'm not going to say all those numbers. Whereas the placenta, with respect to time, in the same time period, is negative 168, a lot of numbers, grams. And you might be thinking, why is the placenta a negative weight? That is impossible. Well, the reason being is that in a biological sense, the fetus develops before the placenta. And since we're measuring in the same time period, see, at 16 weeks, the fetus is already developed into a certain amount of weight, whereas the placenta hasn't even developed yet. But there will reach a certain point where the development of the placenta will start, just not in this time period. A different study was conducted and looked at the effects of exercise on pregnancy. The results in the chart right here summarize the average volume of placenta at several weeks of gestation in non-exercising mothers, starting with the time of 0. And after plotting displaying the polynomial equation, we can see that when t equals 0, the placenta volume equals a negative 15,396 milliliters. And obviously you can never have a negative weight or volume in general, therefore it doesn't make sense. And in a realistic sense, when t equals 0, it should equal 0 as well. Comparing placental weight with the placental volume, we can definitely come to the conclusion that finding the inflection points are done in the same procedure. You take the polynomial equation from displayed on the graph, take its derivative, and find the point of the derivative that crosses the x-axis in order to find the inflection points, as so. And since the placental volume has a figure like this, it would only have one inflection point, whereas since, as shown in the placental weight, it had a little curvature going on, so that's why it had 3 whole inflection points. In order to interpret them into, weeks, we also had to just divide them by 7 in order to, represent the 7 days of a week. And then we just came to the conclusion to estimate that it's about 15, 41, 16 weeks for the placental weight, whereas in the placental volume, it's just about 5 weeks.